Hello friends, welcome back to my YouTube channel. In the 19th part of my discussion on mass transfer coefficients, I will continue discussing interface mass transfer, and today I will be discussing a numerical example. And in this numerical example, you will learn how to find out interfacial concentrations and mass transfer flux in interface mass transfer. So in part number 18, I had discussed one numerical example where I discussed how to find out interfacial concentrations and then mass transfer flux. But in that example, an equilibrium relationship was known to us. And in this particular example, instead of the equilibrium relationship, we are provided with the equilibrium data. So we will be learning how to use that equilibrium data to find out interfacial concentrations and mass transfer flux in a typical interface mass transfer operation. So let us begin the discussion. To start with, we will look at the numerical statement. A weighted wall absorption tower is fed with water as the wall liquid and ammonia air mixture as the central core gas. At a particular level in the tower, the ammonia concentration in the bulk gas is 0.8 mole fractions, and that in the bulk liquid it is 0.05 mole fraction. The temperature is 26.7 degrees Celsius and pressure is 1 standard atmosphere. The individual mass transfer coefficients are given. Kx is 1.59 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. Ky is 1.47 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. The equilibrium data is given in the following table. So you have a table. We have different values of Xa, where in this case A is representing ammonia, and we have mole fractions of ammonia in the liquid phase, and in the gas phase we are provided with the partial pressure of ammonia, which is given in Newton per meter square. So you have different values for mole fractions in the liquid phase, and then you have corresponding values for the partial pressure, which are in equilibrium with the mole fractions. So this is the equilibrium data that is provided to us, and we have to find out the interfacial concentrations and the mass transfer flux. So in this case, the problem is absorption of ammonia from the ammonia air mixture, and this is carried out in a weighted wall column. So I'll just try to show you the operation. So they say a weighted wall absorption tower, it is fed with water as the wall liquid. So water is sent through the weighted wall column as the wall liquid, that is, it is flowing past the wall of the weighted wall column or weighted wall tower. So this is water is flowing down as a thin film, and then ammonia plus air mixture, it is blown as a central core gas through the center of the tower. Ammonia plus air mixture is passed, and as water and ammonia air mixture comes in contact with each other, there is absorption of ammonia into water. So here ammonia is denoted by A. So this is A plus air mixture, that is ammonia plus air mixture. So for this particular problem, at a particular level in the tower, the ammonia concentration in the bulk gas phase, it is 0.8 mole fraction, and that in the bulk liquid phase it is 0.05 mole fraction. The temperature is 26.7 degrees Celsius and pressure is 1 standard atmosphere. The individual mass transfer coefficients are given to us. Kx is 1.59 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. Ky is 1.47 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. And the equilibrium data is also provided. So we have mole fractions of ammonia in the water phase in equilibrium with partial pressure of ammonia in the ammonia air mixture. So I hope you have understood what is given in the numerical statement. If you have any doubts, you please mention them in the comment section. Let us move ahead. First of all, we will collect the given data. The mass transfer problem in this case is absorption of ammonia, which we have denoted by capital E. Absorption of ammonia from its mixture with air in water. Then bulk phase concentrations, they are given to us. YAG is 0.8. Concentration of E in the bulk gas phase, YAG, it is 0.8. Then concentration of ammonia in the bulk liquid phase, it is given, it is 0.05 mole fraction. Temperature is 26 degrees Celsius, 26.7 degrees Celsius, which is 26.7 plus 273.15, which is 299.85 Kelvin. We don't need temperature in our calculations, but I am listing what is given to us. Then pressure is also given to us. It is 1 standard atmosphere, which is nothing but 1.013 into 10 to the power 5 Newton per meter square. We need this in our calculation. Then individual mass transfer coefficients are given to us. Kx is 1.59 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. And then Ky is 1.47 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. The equilibrium data is given to us. We have mole fractions of E in water, that is Xa, and then partial pressure of E in its mixture with air, which is Pa. So Xa is in equilibrium with Pa. So all those equilibrium data, equilibrium values, they are given to us. And what to find? We are supposed to find the interfacial concentrations, that is Xai and Yai, and then we have to find out the mass transfer flux, which is ENA. So whatever is given to us, I have listed over here, and based on that information, we are supposed to find out interfacial concentrations, Xai and Yai, and the mass transfer flux, that is ENA. So let us continue with this. Now first let us understand what is our approach for solving this numerical. So first we will have to convert the equilibrium data into required form, because whatever is given to us, we have to change it to the required form. We need concentrations in terms of mole fractions. In the liquid phase, it is in mole fraction, so there is no need to do anything with that. But the concentration in gas phase, it is given in terms of partial pressures, and we have to convert it to mole fractions. So mole fraction of A in water, Xa, it is given. There is no need to do anything with this. But partial pressure of E in its mixture with air, it is given, and we have to convert it to Ya, the mole fraction of ammonia in the air mixture, in its mixture with air. And after we convert that data into the required form, we will be plotting the equilibrium diagram, and that equilibrium diagram will be plotted by using the equilibrium data, the converted equilibrium data. And then after we plot the equilibrium diagram, we will be drawing the driving force line, or we will be plotting the driving force line. And then after the driving force line is plotted, we will be getting Xai and Yai, because these will be the constant coordinates of the point of intersection between the driving force line and the equilibrium curve. And then after that, finally, we will be calculating the mass transfer flux, that is ENA. So we will be getting the solution in these steps. I hope the steps are clear to you. If you have any doubts, you please mention them in the comment section. Let us move ahead. Now let us start solving this numerical. So first step is we will be converting the equilibrium data, the given equilibrium data, into required form. So we need mole fractions of E, XA and YA. XA is, they have given us XA and PA. So XA is already there. We need to convert PA into YA. That is PA, the partial pressure has to be converted to YA. And let us understand how to do that. So I will just collect the data. So we will be getting values for Y. So XA values are given to us and corresponding PA values are given to us, partial pressure in Newton per meter square. Now let us get the corresponding values for Y. And for that, we are going to use the Dalton's law, which states that partial pressure of A is equal to mole fraction of A in the gas mixture into total pressure. And from that you can get mole fraction of A as partial pressure of A divided by total pressure. So for the first reading where XA is 0 and partial pressure is 0, so PA is 0, total pressure it is given to us, it is 1.013 into 10 to the power 5 Newton per meter square. YA in this case will therefore be 0 upon 1.013 into 10 to the power 5, that is 0. Now let us check for the second reading. For the second reading, PA is 7171 Newton per meter square. So therefore in this case YA will be equal to 7171 divided by 1.013 into 10 to the power 5, that is 0.07. So for PA is equal to 7171 Newton per meter square, YA is 0.07. So you can follow the same procedure to get the other values for YA. So I will just take all those values, 0.13 and then 0.59 and then finally we have 0.92. So in this way, we have converted the given equilibrium data into the required form. Now we have XA values in equilibrium with YA values and we will be using these values to plot the equilibrium diagram. Let us move ahead. If you have any doubts, you please mention them in the comment section. Let us move ahead. Now the second step is we will be plotting the equilibrium diagram. So for that, on the x-axis we will be plotting XA and on the y-axis we will be plotting YA. On x-axis the scale is 1 centimeter is equal to 0.05 and on the y-axis the scale is 1 centimeter is equal to 0.1. So if the equilibrium data is plotted, we will get the equilibrium curve. So in this way the equilibrium curve has to be plotted. Now after we have the equilibrium curve, first task is we will be locating the point in the bulk. So let that point be denoted by P and it will be having coordinates of XAL and YAG. XAL is given to us, it is 0.05. YAG is also given to us, it is 0.8. So let us locate it. XA is 0.05 and XAL is 0.05 and YAG is 0.8. So point P will be located over here. Now next task is we have to plot the driving force line, and for plotting the driving force line we will be using its slope, which is given as minus kx upon ky. Kx is given to us, it is 1.59 into 10 to the power minus 3 kilomole per meter square per second per mole fraction, and ky is also given to us, it is 1.47 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. So therefore slope will be equal to minus 1.59 into 10 to the power minus 3 divided by 1.47 into 10 to the power minus 3, which comes out to be minus 1.08. So now the driving force line will be plotted with a slope of minus 1.08. So let us do that. Now we need to understand this thing. Let us learn how to plot the driving force line. Now see, if you try to find the relation between scale on the x-axis and scale on the y-axis, you will come to know that scale on the x-axis is, or scale on the y-axis is 2 times the scale on x-axis. So that is x is equal to y upon 2. And now I will be using the definition in order to get the driving force line of the required slope. I will be using the definition of tan theta. Now in our case, the line is of negative slope. So the line will be plotted like this. And for that, so this will be the slope, the angle made by the line with the positive x-axis. This is x-axis and this is the negative y-axis. The slope is the angle made by the line with positive x-axis. So this is theta. So now tan theta in this case will be defined if I complete this triangle, which is a right angle triangle. Let us see, M N O. So in this triangle, tan theta will be defined as NO, distance NO, by MN. Now what I will do, I will make MN to be 1. Or let us the relation is, this is x. So if you are traveling 1 unit in the horizontal direction, you will have to travel half of the slope. Slope is 1.08, but since scale is the scale is having this relation, so while traveling in a vertical direction, we will have to travel half of the distance, half of that, we will have to travel a distance which is equal to half of the slope in a downward direction. Why downward direction? Because the line is having a negative slope. So we will be traveling 1 unit. We will be traveling 1 unit towards the right, and then a distance equal to half of the slope in a vertical downward direction. Why half of the slope? Because the scale that we have chosen, the scale on x-axis and y-axis, they are related by this relation, y is equal to 2x. So that is x is y upon 2. So we on the y-axis, in the vertical direction, we have to travel a distance that is half of the slope. So if we do that, we are going to get the line of the desired slope. So let us do that. So I am traveling 1 unit in the right direction horizontally, and now half the distance, half of distance equal to half of the slope value. So that is it is 1/2 will be 0.5, around 0.5. So I have traveled that distance. So I get this point. So if I draw a line that passes through P and this point, I will be getting a line which is having a slope of minus 1.08 on this graph. So I hope it is clear to you. I hope how to plot the operating line, the driving force line of the desired slope, it is clear to you. Please note that since we have used different scale on x and y axes, we are using this approach to plot the operating line. So I hope the concept is clear to you. If you have any doubts, you please mention that in the comment section. Let us move ahead. So after that, we have to get XAI and YAI. So when we plotted the driving force line, we have got intersection of the driving force line with the equilibrium curve. So the coordinates of that point are XAI and YAI. So point M is located at the point of intersection of the driving force line with the equilibrium curve. So this is the point M. And the coordinates of point M are XAI and YAI, as I told you. So if you get the X coordinate, it comes out to be 0.25. So XAI is 0.25. And if you get the Y coordinate, it is 0.59. The Y coordinate, actually it is 0.585. So XAI is 0.25 and YAI is 0.585. So in this way, we get the interfacial concentrations. So solution to part 1 is complete. We have got the values of interfacial concentrations. Now let us get the mass transfer flux. So I hope the step is clear to you. If you have any doubts, please mention them in the comment section. So after getting the interfacial concentrations, now let us get the mass transfer flux, that is NA. And for that, we will use equations for both the phases. For gas phase, the equation is NAG is equal to KY into YAG minus YAI. So KY is given to us, it is 1.47 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. YAG is also given, it is 0.8, and we have found out YAI, that is 0.585. So NAG will be equal to 1.47 into 10 to the power minus 3 into 0.8 minus 0.8585. That gives us NAG as 3.16 into 10 to the power minus 4 kilomole per meter square per second. Now let us use the equation for the liquid phase. So for liquid phase, the equation is NaL is equal to Kx into XAI minus XAL. XAI is 0.25, we have found out. XAL is 0.05, which is given to us. And Kx is 1.59 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. So therefore, NaL will be equal to 1.59 into 10 to the power minus 3 into 0.25 minus 0.05. So that gives us NaL as 3.18 into 10 to the power minus 4 kilomole per meter square per second, which is almost equal to NAG. So in this case, for this particular mass transfer problem, the mass transfer flux is 3.18 into 10 to the power minus 4 kilomole per meter square per second, which is equal to which is almost equal to 3.16 into 10 to the power minus 4 kilomole per meter square per second. So with this, we get the complete solution. We have got the interfacial concentrations, and then we got the mass transfer flux. So with this, I will end my discussion for this video lecture. So in this, I hope you have learned how to find out the interfacial concentrations and the mass transfer flux in interphase mass transfer when equilibrium data is given to us. In the previous example, in my previous video lecture, I had discussed a similar example where an equilibrium relationship was given to us. So I hope you have seen that video. I am giving link to the entire playlist of my video lectures on mass transfer coefficients in the description section. You please watch all those videos. Tell your friends to watch them. And for now, for this video lecture, I will end the discussion. Thanks for watching the video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. In my next video lecture, I will be discussing the overall mass transfer coefficient, and then I will be deriving a relation between overall mass transfer coefficient and individual mass transfer coefficients. So hope to see you soon in that video lecture. For now, have a nice day. Take care. Bye bye.